Hello everyone, we are given the asymptotic Bode magnitude plot of a minimum phase transfer function g of s. Also, we are given two statements. Statement 1, transfer function g of s has 3 poles and 1 0, and statement 2, at very high frequency the phase angle equals minus 3 pi by 2. We are asked to find the correct option. To know more about the concepts used to solve this problem, kindly refer the NPTEL Control Engineering course Week 6 Lecture 4 by Professor Ramakrishna Pasumarthy of IIT Madras. We'll be using the following concepts to solve this problem. The asymptotic Bode magnitude plot shows the magnitude response of a system at different frequencies. The Bode magnitude plot can be used to identify the system, that is, find the poles, zeros and the DC gain of the system. The phase contribution of a pole at infinite frequency is minus pi by 2 radians, and that by a zero is pi by 2 radians. I have drawn the Bode magnitude plot here. So statement 1, we are asked to find the number of poles and zeros. So we'll first find the general form of the transfer function. Looking at the initial part, we can see that there is a minus 20 dB per decade. So from which we can infer that there is a pole at the origin. That is 1 by s. Next, the slope further decreases by minus 20 dB per decade and becomes minus 40 dB per decade after frequency of 1. So we'll take it as omega 1. So this is the first corner frequency. So which implies there is a second pole at 1 plus 1 by st1, where t1 equals 1 by omega 1. And then again at this frequency, let us take it as omega 2, the slope further decreases by minus 20 dB per decade. So we can infer that there is another pole contribution after this frequency. So there is a third term 1 by st2, where t2 equals 1 by omega 2. And there will always be a constant DC gain term k. So now we can write the general form of the transfer function. That will be g of s equals k divided by s times 1 plus st1 times 1 plus st2. That is the general form of the transfer function. Now, as for statement 1, we can see that there are no zeros. So number of zeros is 0 since there are no zeros here, and the number of poles equals 3. So which means that statement 1 is false. As for statement 2, we'll again write the transfer function in its j omega form. So we'll substitute s equals j omega. Here, then we'll get j omega 1 plus j omega t1, 1 plus j omega t2. Now let us find the phase of the system. So phase of g of j omega equals phase contribution by the constant term is 0. Then the phase contribution of 1 by j omega is minus pi by 2 for all frequencies, since there is no real term here. Then the phase contribution of this pole, that will be equal to minus tan inverse the imaginary part omega t1 divided by the real part, which is 1. Same for this pole, so it will be minus tan inverse omega t2. Now we are asked to find what happens to the phase at infinite frequency, that is omega tending to infinity. So we'll set the limit for this phase of the system, that is as omega tends to infinity, g of j omega equals, this will remain minus pi by 2 minus, so as omega tends to infinity, the tan inverse will tend to pi by 2. So it will be minus pi by 2. Same for this case. So there will be minus pi by 2 again. So that will be equal to minus 3 pi by 2. So statement 2 is in fact true. So statement true is true. Looking back at the options, we find that the correct option is option B. Statement 1 is false and statement 2 is true. Thank you.